Well, welcome to the third lecture on the third Millennium problem. Before we the next lecture, the fourth one is today, on the 28th of March, because of spring break, a longer interval. And for any newcomers, don't forget the refreshments down in the eating area over there and down after the talk. Our Lorenzo Sadun, our speaker tonight, is our first American-born speaker in this series. He's an associate professor of math at UT, which probably doesn't surprise you that he's here. When I consulted people about what to say in this introduction, there was remarkable unanimity saying, that one thing I should mention is his great problem-solving ability. If you're a mathematician and run across a problem in your research that you can't solve, the excellent strategy would be to tell Lorenzo about it. This talent was already evident, probably even before that, but certainly when he took the Putnam exam as an undergraduate at MIT. Maybe I should say a few words about the exam for the people who don't know about it. William Lowell Putnam was a wealthy Boston financier who about 80 years ago got the idea that if it's good for colleges to compete in athletics, it might be even better if they'd compete in academics. And he wrote about that, but apparently didn't do much about it. But after he died, his wife endowed a trust fund in his name, in his honor, to promote this idea. And in the this was around 1930, and for a few years in the 30s, there was an English essay competition, but somehow that didn't catch on, and the permanent result of her bequest has been that since the time of World War II, there's been a yearly math exam, the Putnam exam. It's 12 questions which test originality as well as mastery of the technique of undergraduate mathematics. And the colleges compete by putting up three-man teams, but students can also compete individually. Can just enter individually. Lorenzo took the exam in 1979 and placed 12th. That's 12th out of 2,141 contestants from 388 colleges in the U.S. and Canada. That's an amazing, really impressive performance, but I might not have thought it worth much. It's just as an undergraduate, it's undergraduate math. I might not have mentioned it, except for the amazing coincidence that I'm going to be able to say the exact same thing about one of our other speakers, who took the exam at Harvard at the same time Lorenzo took it at MIT, and those two and one third person ended up tied. It's true. You can look. It's recorded. Well, they don't publicize the exact scores. But anyway, Lorenzo tells me that they missed 10th place. So they were 11, 12, 13. They missed 10th place by 1 point. Anyhow, so that's really amazing. They both ended up here. There are two of them. But anyway, to get beyond Lorenzo, well, Lorenzo actually, he excelled in non-academic things also as an undergraduate. He and his roommates are known for a typical MIT undergraduate prank, which was no mean feat. Took a long. They had to try. They succeeded on the fourth try to avoid being frustrated by the campus police. But it's too long a story to go into here. And to get beyond that, his undergraduate days, he did his. He got his PhD from UC Berkeley, although he wrote his thesis at Harvard, where his advisor, Cliff Taubes, had moved while he was a graduate student, so he went to Harvard with Taubes, finished there. He came here after postdoc positions at Caltech and NYU, at the Courant Institute at NYU. He's held a National Science Foundation postdoctoral research fellowship and has several teaching awards. In his research, he has unusual breadth and talent. He thrives on collaboration and interaction. This brings out the best in him, and he brings out the best in others. Broad is certainly true. Things his interest, his research work ranges from physics to topology and to pure math, topology and group theory. Things he's worked on include relativistic quantum field theory, Yang-Mills, partial differential equation, fluid dynamics, knot theory, plane tilings, group theory. So he's really amazingly broad. He doesn't play the guitar, but he does juggle, and I'm told he plays soccer quite seriously. He also has had wide knowledge and interests outside of math. I mean, he pointed out to me that he's the first Millennium problem speaker of the Millennium by the Julian calendar. When I didn't understand, he had to explain to me, I was embarrassed, some basic calendar history and point out that sept is 7 and oct is 8 and nov is 9 and dec is 10. And that for most of the history of the last couple of millennia, March was the first month of the year. Well, I've talked long enough. Let's greet Lorenzo Sedan, who will talk on Yang-Mills and the mass gap. Lorenzo.
Thank you. Well, I want to tell you about Yang-Mills theory, and Yang-Mills is two people. There they are, C.N. Yang and R.L. Mills. And what they did is they put together this theory of strong and weak nuclear forces about 50 years ago. And this is the basic construct that has been used for many of the developments in particle theory and subatomic physics, in the last 50 years. And so my goal today is to tell you what is Yang-Mills theory and what is a mass gap supposed to be. I'm not going to tell you very much about what people have done to try to solve the problem, but I do hope to get across what is the problem. We'll have to settle for that. Now, assume you've read this so I don't have to read it. The quick outline of what we're going to do, I could tell it to you in a minute. I mean, Yang-Mills theory is this theory that grew out of geometry. It's differential geometry, and at the same time out of modern physics, especially out of quantum mechanics. And it's really an extension of the ideas that explain electricity and magnetism. I mean, electricity and magnetism was done a long time ago. And so these ideas extend that. But there's a difference between nuclear forces and electricity and magnetism. Electricity and magnetism extends over large distances. Nuclear forces extend over very short distances. Why? Well, it has to do with this mass gap. And so the basic problem is come up with a sound mathematical statement of what is the theory and show it has a mass gap so that things are short range, and then you're done. So if you're satisfied with that outcome, I would say that you can leave, but the refreshments won't be served for another hour. So instead, we'll move on to 59-minute outline. So what I want to do is I want to talk about what is the development in physics. What is the physics that we have to explain using Yang-Mills theory? So we'll talk about 150 years of physics, and then I'm afraid the math gets shortchanged. We only get 100 years of math. And then we'll see what Yang-Mills theory actually is, and we can ask, what's the problem and where do we stand? How close are we to solving it, or what remains to be done, and who's about to do it? So, first character in our story is Charles Coulomb. He's the guy who came up with the law of electricity. If you take electric charges, you put them together, like charges repel, opposite charges attract. Okay, no big deal, except he quantified it. He said the force between two charges is proportional to their product and drops off like the distance squared. You move them twice as far apart, you get a quarter as much force. Okay. Now that sounds like something that dies off with distance. I mean, you're dividing by r squared. But there's really something very special about 1 over r squared as opposed to, say, 1 over r cubed or 1 over r to the fourth or e to the minus r or log r. I mean, you can write down all sorts of force laws, which is that it's not really getting weaker with distance. It's getting weaker with distance because you're measuring it at just one point. So you could ask, what's the total amount of force field that this charge is giving off? The total amount of force field, well, and you can measure the field. It's called the electric field, given off by an electric charge. And you ask, how much electric field is there out at a distance r? Well, the field is dropping off like 1 over r squared, but you go twice as far and the sphere has 4 times as much area. So the total amount of, it's called flux, the total amount of electric field going out through the sphere isn't dropping off with distance at all. It's staying constant. So what that means is the force field, you shouldn't think of it as dying off. You should think of it as spreading out. Okay? It's got more ground to cover, so of course it's less intense at every point. But there's just as much of it farther out as there is close up. I mean, you can imagine something that gets absorbed by the air and gets weaker and weaker and weaker as it goes out. That's not this. 1 over r squared is something that is, it can extend as far as you like, but if it's spherically symmetric, it's going to spread out and so take up more area and so get weaker. So this is a very special thing about 1 over r squared. And whenever you see a force that's 1 over r squared, we're going to call that a long-range force because it doesn't die off. Another example of a long-range force is gravity. Same 1 over r squared law, and I think we can agree that gravity has some important applications at fairly large distances. So that's the law of electricity. And that's great. So they figured out electricity, and somebody else went out and figured out some rules about magnets and figured out that, if you have a charge that's moving, then that sets a magnetic field. And somebody else figured out that if you have a changing magnetic field, then that gave you a force that generated currents. And you had a bunch of rules that people figured out about electricity and about magnetism. And the guy who put it all together was James Clerk Maxwell. And he put them together and he wrote down the equations and he said, these equations, they're waves. The equation suggests there's some sort of waves, and he worked out how fast the waves would go, and he discovered that these waves are moving with the speed of light. Aha! Maybe light is just a property of electricity and magnetism. We can scarcely avoid the conclusion that the light consists of transverse undulations of the same medium which is the cause of electric and magnetic phenomena. So Maxwell has this bright idea. He not only put together all the laws of electricity and magnetism, but he realized that light has something is extremely closely connected to electricity and magnetism. It's not just optics, that there are these particles of light beaming down on you. It's electricity and it's magnetism moving in a particular pattern, in a particular wave-like pattern. Or to put it more simply, and I'm a card-carrying ACLU member, and I promise this will be the last theological reference in the talk. Okay, so there are the equations of electromagnetism. They're called Maxwell's equations, and the specific form of the equations is not important to us. But there are some equations. That's nice. What is important to us is some properties that they give us. That it turns out that you can write all the equations, instead of in terms of the electric and the magnetic fields, you can write it in terms of what's called a potential. They usually write the letter A for the potential. And the potential satisfies this particular equation. Now, again, it's not important to look at the details of the equation, except take my word for it, this is called the wave equation. Anything that satisfies that equation, you can fiddle with that constant. It's the same equation that describes the propagation of sound, or most other kinds of waves, just with a different constant there. The constant there is the speed. In the case of light, it happens to be 300 million meters per second. In the case of sound, it's 300 meters per second. But it's the same equation that governs all of these waves. And the key thing is that anytime you have something that has that kind of equation, it's going to have this long-range property, that it just spreads out, it doesn't die off. But if you had a slightly different equation, if you have an equation that has an extra term in there, then you do get something that dies off. You get something where all the low-energy phenomena, and sure, if you pump enough energy into it, you can get it to spread out. But if it's low energy, it's all very localized. It's localized to within a distance L, roughly. That you go off a distance L and you get a factor of 2.7 weaker. Then you go out a distance L again, it gets another factor of 2.7 weaker. You go out 5 or 10 L and you get ridiculously small size. So something like this we would call a very short-range force that has a length scale of L. And something that, like this, we would say it's a long-range phenomenon and has, well, an infinite range. So that's it for classical physics. It's a crash course here. The next player in the game, get rid of both of these, is Max Planck, who has a constant named after him. And Planck came up with quantum mechanics. The key features of quantum mechanics, this was 1900. He discovered that many of the properties of light could not be understood just applying Maxwell's equations. You had to put in an extra property. And that extra property was that light was lumpy. If you tried to have light of a certain frequency, you couldn't just make it as strong or as weak as you like. You couldn't have an arbitrary amount of energy into it. The amount of energy that you could get out of the light, or that you could put into the light, came in units of proportional to the frequency, a certain constant called Planck's constant times the frequency. And you could have 1 unit of energy, or 2 units of energy, or 3 units of energy, but you couldn't have 13.725 units of energy. It had to be a certain multiple of h nu. So the moral is that things come in single lumps. You could talk about taking out 1 unit of energy, or 2 or 3. It's like each unit of energy behaves just like a single particle. So you had this phenomena that everything was wave-like before, but now Planck says you should think of it kind of, sort of, maybe like a particle. And he found this rather remarkable. If anyone says he can think about quantum problems without getting giddy, that only shows he's not understood the first thing about them. And one of the things that happens over time is that our understanding of things gets simpler and more direct. So about 10 years later, another of the giants of quantum mechanics, Niels Bohr, said the same thing in one sentence. And more recently, certain attitudes don't change. Okay. Next player in the story, Albert Einstein, whose motto here, everything should be made as simple as possible, but not simpler, is basically the story of the night. That I am trying to make things as simple as possible, but there's a limit. So, what is Einstein best known for? Relativity. So, now I'm not going to go through all of the weirdnesses of relativity here. I just want to get one equation out of relativity. Well, maybe two. That is that when things are not relativistic, when you talk about Newton's laws of motion, there's a formula for the energy of a system. It's related to the momentum by energy is momentum squared over twice the mass. That's the kinetic energy. And then you could also have a potential energy, and then you can only really measure differences in energy, so you could add a constant to the thing. But essentially, you should think energy is momentum squared over 2m. And Einstein said, no. In reality, energy and momentum are related by a slightly different formula. And you'll notice that says if there's something is still, it has no momentum at all, you take away the momentum, you get E squared equals m squared c to the fourth, or E equals mc squared. Okay, so there you have, at the heart of relativity, a useful formula which you can now forget about, but we'll bring it back. You can forget about it for a few minutes until we see it again. That's one of the ingredients that we're going to have for the development of the mass gap. Next player, Louis de Broglie. Actually, I don't know how you pronounce his name. I'm told that almost anybody who pronounces his name almost any way is doing it wrong. There must be a right way, but I've never heard it. What de Broglie said was something to the effect of, well, look, if waves behave like particles, why shouldn't particles behave like waves? So whenever you have a particle, if you've got an electron or a proton or a bowling ball, I mean, any of these should be described by a wave. And he says, everything is waves, and the energy goes as the frequency with which the wave is oscillating. The exact same formula that Planck used for light. And the momentum is related to the wavelength. So if you have a bowling ball going across, well, it's got an awful lot of momentum. It's got enough to knock a few pins down. So it's got a very, 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 very tiny wavelength, and you'll never be able to actually see the fact that it's oscillating. But it's still a wave. And if you've got an electron, well, that's a lot lighter. It's got much less momentum. It's got a much bigger wavelength. You should be able to see its wave-like properties. So he's got this great theory. Everything is waves. And so everything is waves and everything is particles. And that sounds really, really weird. But Planck and Bohr already told you, yeah, so it's weird. Quantum mechanics is weird. Two seemingly incompatible conceptions can each represent an aspect of the truth. They may serve in turn to represent the facts without ever entering into direct conflict. The real moral of the story is you shouldn't think about it's a particle, it's a wave. You get half the room yelling one at the other half of the room yelling the other. It's not the way it is. It's that to everything is described by some equations, and the equations happen to be wave equations, but everything comes in certain units, so it's in some ways behaves like you're used to thinking of particles, and in some ways it behaves like you're used to thinking of waves, and you've got certain mental constructs that you're hung up on, and I'm hung up on, and everybody who's grown up in the regular world is hung up on, that are only an approximation to what's really happening there in subatomic physics. And thinking of them as particles gives you some insight. Thinking of them as waves gives you some insight. Don't ask yourself, is it one or is it the other? It's kind of like one. It's kind of like the other. That's life. Anyway, we're back to the question. We got these waves. Your waves are supposed to have some equation to tell you how they go up and down and how they move around and what's supposed to go on. And the guy who came up with the equation is Schrodinger. I don't have a quote from Schrodinger. But Schrodinger said, here's the rule for how to get an equation. Now, unfortunately, the equations get a little bit complicated. You need to use calculus. You need to use complex numbers. So he said the equation involves this wave function, psi of x, which at every point in space you've got a complex number associated to that point in space. And the size of that complex number has something to do with what's the probability of finding the particle here or there or somewhere else. And you want to know what the equation is that's satisfied by this wave function. What you do is you take the usual equation that you have for energy and momentum, and whenever you see an energy, you replace it by IH bar times the derivative with respect to time, where h bar is the same constant we had, Planck's constant, only divided by 2 pi. You get lots of 2 pi's in the formulas. It's useful to just absorb them into the constants. And by I is the square root of minus 1. We're dealing with complex numbers. There's no getting around the square root of minus 1. And momentum is replaced by a derivative in the momentum in the x direction is replaced by a derivative in the x direction. Momentum in the y direction is replaced with a derivative in the y direction. And so you just slavishly, wherever you see an equation, every time you see an e, replace it with a time derivative. Wherever you see a p, replace with a space derivative. So if you start off with e is p squared over 2m, you get I times the time derivative equals, well, I squared is minus 1 times constant times a space derivative. So there you get an equation that this is supposed to satisfy, and that's Schrodinger equations. So Schrodinger came up with this prescription of replace energy and momentum with derivatives, and you apply that to non-relativistic, you apply it to Newton's laws, and you get Schrodinger's equation. And then you go ahead and solve this equation. You figure out all sorts of things. You figure out the energy levels of the hydrogen atom, and it all comes out beautifully. And you solve all sorts of problems in physics in the 1920s, and everyone's real happy. Until somebody stops and says, well, yeah, that's nice if things are moving slowly, if they're not relativistic. But Einstein told us there's relativity. How are you going to take relativity into account? So relativistically, we said this is how energy and momentum are related. So the deal is wherever you see energy, replace it with a time derivative. Wherever you see momentum, replace it with a space derivative. So you get this equation, which is called the Klein-Gordon equation. And let's see, if you divide both sides by h bar c squared and by minus h bar squared c squared, you get this equation, which you may recognize. I told you could forget it for a little while. I didn't say you could forget it forever. I'll pull it back. That's exactly this equation. Remember, I told you that light satisfied a certain wave equation, but if there were this extra term, it would die off quickly. Well, from quantum mechanics comes exactly that equation, and the rate at which it dies off has something to do with the mass. So, things die off. If you have a particle which has a mass, then things die off, and the typical length has to is 1 over the mass. So if you have a very light particle, it spreads out a decent distance. A heavier particle will be a much shorter distance. If you have a particle that doesn't have a mass, if this term is gone, then you get the wave equation, and everything spreads out. So this is the mass gap of the Yang-Mills equation, Yang-Mills existence and mass gap. Just told you what the mass is. If you've got masses, if you ever have something like light only with a mass, then it'll be short range. If you have something like light but without a mass, then it's going to be long range. And so the mass gap problem is figuring out why the things that play the role of light when it comes to nuclear forces have a mass. Now, trouble is I've given you part B of the problem without part A. I haven't told you, what are you doing with nuclear forces? You know, what is this object that's supposed to sort of, kind of, maybe play the role of light? You know, we know what mass gap is, but we don't know what Yang-Mills is. So for that, we're going to have to take a digression. So we've had our 150 years of physics. Ready for an exam? Okay. Well, you hereby pass your physics course. Time for a math course. So we're going to go back 100 years to the development of non-Euclidean geometry. Now, the idea of non-Euclidean geometry has to do with the notion of parallel lines. Suppose I look at these two vectors and I ask, what's the angle between those two vectors? I've got a vector here at this point and another vector at a different point. How am I ever going to figure out the angle between them? Well, there is a way, but it involves parallel lines. The first thing you do is you draw the line, which I've already drawn in dotted lines, along one of the vectors. And then you say, aha! Euclid's parallel postulate says that whenever you have a parallel line and another point, I can draw a line through that second point that's parallel to the first line. And then all I do is I measure the angle over here. I don't have to compare things at different points. I just have to compute this angle right here at this one point. Great. So if you have a notion of parallel lines, then you can compare vectors at different points. But if you don't have a notion of parallel lines, you're in trouble. So in fact, on most spaces that you're interested in talking about, there is no consistent notion of a parallel line. That means that there's no way to talk about you can talk about the angle between two vectors at the same point, but you can't talk about comparing vectors at different points, and you can't say what is the angle of a particular vector. There's no consistent reference standard that you could carry around from point to point. Now this is a little weird, so I brought a demo. So here's a space that we'll talk about the surface of the basketball, and I think most of you would agree that this is not flat. Well, it's a little flat. I didn't put enough air into it. But so let's take a point, and let's take a vector at that point. And let's see what happens if we try to move that around. Now, it is true that there's no universal notion of moving things parallel, but you can drag things along a path. So suppose I wanted to go along this path and keep that vector as parallel as it possibly could. Where would the vector be pointing when I got to this point? Straight down. There we go. Just rotates like that. No big deal. Okay, now let's suppose we want to drag it around over here. It's pointing south. I want to move it around. Well, it's pretty clear that I want to wind up with a vector over here that's pointing south. So move this around, and there you go. It's pointing south. So I move this vector to here and to here. Now what happens if I try to bring it back up to the North Pole? It wants to move up this way, which means it wants to come up, come up, come up, come up, come up. Oops. Okay. The point is that if you try to move things, there's no notion of parallel. There's no way to come up with a consistent reference at every point in space. And if you move around, things tend to twist. Now, I think most of you would agree that a basketball is curved. This twist is exactly what we mean mathematically by curvature. So, on a sphere or on any other curved space, vectors you can move vectors along paths, but as you move them along a path, they tend to twist around. Now, I brought that vector along a very big triangle, and it rotated by 90 degrees. If I'd moved it around a little triangle, it would have rotated by only a few degrees. in general, it turns out that the amount that they twist, if you're on a sphere of radius r, turns out to be the area of that triangle divided by r squared. So if you move things around on the surface of the Earth, if I want to get a 90-degree twist on the surface of the Earth, I'm going to need an awfully big triangle. I can't do it by taking a vector and moving it over there, and then back over here. I'm going to have to take it here, move it to South America, move it to Africa, and move it back to the United States. So the Earth is very big. 1 over r squared is very small. The Earth is curved, but it's a very small curvature. It's almost flat, which anybody who's been to, say, Lubbock knows what almost flat means. But in general, curvature is the amount that vectors twist per unit area. And so on a sphere, curvature is 1 over r squared. And on a plane, there's no twist. You move things around, you can pick up a vector and move it to any other point. There's no twist at all. The curvature is 0. You can also talk about spaces where the curvature is negative. Negative curvature means the vectors twist the other way. And so, in fact, I think in the first 2 Millennium lectures, there was a discussion of hyperbolic spaces. Those are spaces where the curvature is negative. They come up a fair amount. And if you take a typical space, the curvature isn't a constant. The sphere has the property that curvature is constant everywhere. On most spaces, it isn't. Like if you just had a donut, that's something where the curvature actually is positive on the outside of the donut, where you take the first bite. And it's negative on the inside of the donut, where the hole is missing. It's not constant. Okay. So that's 2-dimensional spaces. Now, those of you who were here for the first lecture, you heard all about 3-dimensional manifolds. If you're in a 3-dimensional space, it's a lot more complicated. You can't describe a twist by a number. If I go from this vector to that vector, what number is that? Well, I've rotated, but I've rotated by a certain angle around a certain axis. Things twist in 3 or more dimensions is a lot more complicated than describing rotations in the plane. Rotation in the plane is just a number. In 3-dimensional space, it's more complicated, and so instead of curvature being a number, it's a bigger object called a tensor. But you still have the idea that curvature is the thing that measures how much things twist by when you move them around, when you move vectors around. And that's what tells you whether an object is curved or not. Now, the people who worked this out, I'm sorry, I think I put up the sort of the gods of the development of geometry already, but the people who worked out the ways of measuring the curvature are Christoffel and Levicivita and Ricci. What they did is they had this notion of a covariant derivative. Now, I'm afraid that for those of you who are allergic to calculus, the rest of the hour is going to get a little bit difficult. But the idea is that you can write down an extra piece. When you're taking a derivative, there's an extra piece you can add to it called a Christoffel symbol that keeps track of the twisting. So whenever you would be inclined to take a derivative, you apply a covariant derivative, which is just the regular derivative plus the Christoffel symbol. And from the Christoffel symbols and from the derivatives of the Christoffel symbols, there are formulas for the curvature in terms of the Christoffel symbols. And we don't need to know what those formulas actually are. Well, they need to know what those formulas are, but we don't. The important thing is that there is this whole machine for describing geometry on curvy spaces in terms of Christoffel symbols. And curvature, which is this twistiness, can be computed from the Christoffel symbols. Now, this would be something of a mathematical curiosity, except for Einstein again. Remember Einstein, everything should be as simple as possible, but not simpler. Well, the world ain't simple. You are used to thinking of the world having 3 spatial dimensions, that away, that away, that away, and then time marches on. Now, Einstein says it's more complicated than that. That the world is 4-dimensional. At any point you can talk about 3 space dimensions and 1 time dimension, but it's not a flat 4-dimensional object. It's a 4-dimensional space that is curved in the sense that if you take a vector, You move it around, you move it around, you move it around, bring it back to where you started, it's twisted. And that this curving has everything to do with gravity. That if you describe the curvature of space using covariant derivatives of Christoffel symbols, the gravitational field is exactly a Christoffel symbol. And the curvature is a tidal force. But so Einstein came up with this theory of general relativity in 1916, and if you think about the subtitle of the talk is God a Geometer. Oops, I said I wouldn't. That after Einstein, geometry was all the rage. Wow, he's taken what we thought was a force. The sun is pulling on the earth is pulling on the moon, it's pulling on us. And he's explained that all in terms of geometry. The world is just geometry. And everyone, there was a tremendous sense of, let's see how much we can explain everything in terms of geometry. And in particular, let's see if we just explained gravity in terms of geometry. Let's see if we can explain the other great force, electromagnetism, also in terms of geometry. So, Hermann Weyl came up with a really clever idea for how to explain electromagnetism in terms of geometry. His idea was gauge. What he said is, instead of talking about vectors twisting as you move around, maybe as you move vectors around, they get longer and shorter. That you would have a Christoffel symbol, but it wouldn't talk about twistiness, it would talk about stretching. In order to measure things, you need to have a gauge. And so this whole theory of moving things around is called a gauge theory. And he said that the potential that we talked about for electromagnetism, the thing that satisfies the wave equation, maybe that's really sort of like a Christoffel symbol, only for this stretchiness instead of for this twistiness. And you work out the equations, and you figure out what the curvature is. I said the curvature was a tensor. Well, it has tensor with a bunch of components, the 0, 1 component, the 0, 2 component, the 0, 3 component, the 1, 2, the 2, 1, 3, the 2, 3. And he realized that those components would be exactly the components of the electric field and the magnetic field. The electric field is a vector, so it's described by 3 numbers. The magnetic field is a vector that's described by 3 numbers. The curvature is a tensor that's described by 6 numbers, which is actually these 3 and these 3. Beautiful theory. Only one thing wrong with it. It's wrong. You see, if it were right, then suppose you put an atom in an intense electric field and you had it go around and around and around and around and around. It would come back smaller than it used to be. So you would have some hydrogen atoms that were bigger than other hydrogen atoms. And you can measure the size of an atom. You can see how things like what frequency radiation it emits. There are ways of measuring the size of atoms. And I can assure you that all the hydrogen atoms in the world are the same size. At least the ones in the ground state. The theory just is wrong. There is no stretchiness. You bring things around in a loop, they do not get bigger, they do not get smaller. So the idea of stretching doesn't work. But the idea of building something out of electromagnetism does work. And the thing that makes it work is quantum mechanics. Remember I gave you Schrodinger's equation. And I told you that everything had to do with complex numbers. Well, complex number has, you build a complex number as, a real part and an imaginary part. It's a plus bi, where I is the square root of -1. And I told you that when you have a wave function, the only thing you can measure is the square of the wave function. The square of the wave function tells you the probability of finding the particle. In other words, the length of this complex number. The phase of the complex number is not measurable. It's not directly measurable at all. So there you've got a twistiness. So you can write a theory in which this phase of the complex wave function changes. It rotates. And rotates in how much space? Well, let's see. In the complex numbers, you've got if you think of all complex numbers of a given size, that's all pairs A and B such that A squared plus B squared is a given size. Well, that's a circle. The circle's worth of ambiguity that you can't exactly pinpoint what's the reference. I mean, you can talk about the relative phase of two-wave functions, but you can't talk about the absolute phase of one-wave function. It's exactly like vectors on a sphere. You've got 1 degree of rotation. So you can build a theory in which things are rotating, but they're not rotating in physical space. It's not that they used to be pointing this way, and now they're pointing that way. It's they're rotating in this abstract space. They used to have a particular, it used to be real, and now it's pure imaginary, and now it's negative, and now it's negative imaginary. It's that this number, this complex number is twisting. That in real space, there are only two things you can do. You can rotate vectors, or you can stretch them. And the rotation's already used, and the stretching doesn't work. But if you throw in quantum mechanics, you've got this complex number, and rotating this complex phase gives you this abstract geometry. It's no longer the geometry of measuring lengths and angles on, in the real world. It's measuring this complex number of this field. But that twistiness does work. So you take Weil's idea, and instead of saying covariant derivative is regular derivative plus A, where A is the electromagnetic potential, you say it's ordinary derivative plus I times A, where I is the square root of minus 1. And everything else comes through almost identically with an extra factor of I. The curvature isn't the electric and the magnetic field, it's I times the electric and the magnetic field. And all of Weil's equations come through just fine with an extra factor of the square root of minus 1 coming along for the ride. You don't have to worry about the idea of, you have the idea that if an electron goes around a loop, its phase will change. It'll interfere with itself in some interesting way. But it won't get bigger, it won't get smaller. Nothing, and that is consistent with everything else. And that also tells you how do you incorporate electricity and magnetism into Schrödinger's equation. Wherever you had a regular derivative, just write down a covariant derivative. Now we've got a theory of electrons, and how do electrons respond to electric and magnetic fields, and it's exactly right. This is the correct theory of how electrons respond to electric and magnetic fields. So here's the great geometric idea that electricity and magnetism is geometry, but it's not geometry in the usual sense. It's geometry in this more abstract sense. Okay. Key features of this theory: everything is linear. You're talking about first powers of A. Charges and moving charges give rise to electric and magnetic fields. Electric and magnetic fields act on charges. So charges act on fields, fields act on charges, but fields don't act on fields. In other words, if I took two beams of light and I passed them through one another, the beams of light don't do anything to one another. The light which carries electricity and magnetism, if I put some charged particles in there, they would feel the light. And if I take some charged particles and I move them around, they would generate light. But if I have light passing through light, it just passes through light. It doesn't interact with light. So this is the first great gauge theory. Electromagnetism is a gauge theory. And really was a triumph for geometrical thinking in physics back in the 1920s. Okay. So now we're done with our 100 years of math, and we've done with a bit more of physics. Next question is, okay, what is it that Yang and Mills did? So we go forwards about 20 or 25 years. Now we talk about some nuclear physics in the 1950s. 1950s, people were studying protons and neutrons and mesons. There were pi mesons. There are three types of pi mesons. Some with a plus charge, some that are neutral, some with a minus charge. And the funny thing was that these pi mesons could cause a neutron to turn into a proton, or cause a proton to turn into a neutron, or might be absorbed by a proton, or might be absorbed by a neutron. Pi mesons had something to do with neutrons and protons. And so there was this theory, this mystery of, well, what's going on here? And the idea is called isospin, which is that, of course, you and I can tell the difference between a proton and a neutron. One has charge, one is not. But as far as the nuclear forces are concerned, they basically behave alike. You could really think of them as being two different states of a particle that we'll call a nucleon. So a nucleon has one state which we'll call the proton state, another state which we'll call the neutron state. So if I write down the wave function for a nucleon, I shouldn't write down one complex number. I should write down two complex numbers. I should write down the extent to which it's a proton and the extent to which it's a neutron. So I should write it as a vector with two entries. Well, if I do that, then what happens if I take a vector like that and multiply a matrix like this by a vector like that? Well, the neutron part goes up and becomes the proton part. The proton part disappears. Well, if you hit a neutron with a pi plus, it can turn into a proton. You hit a proton with a pi plus, it doesn't absorb a pi plus. So it says a pi plus behaves kind of like this matrix. A pi minus behaves kind of like that matrix. And a pi naught behaves kind of like that matrix. So everything, instead of becoming complex numbers and multiplied by numbers, becomes these vectors multiplied by matrices. And so the big idea of Yang and Mills was, let's do what Weil did, only let's do it with matrices. Let's take this whole idea of a covariant derivative, and instead of just multiplying by a number, we'll multiply by a 2 by 2 matrix. So in the 2 by 2 matrix, it tells you how things twist in 2 by 2 two-dimensional complex space. Two-dimensional complex space, let's see. Two complex numbers. I've got the real and the imaginary part of the first number, the real and the imaginary part of the second number. It's four numbers I'm talking about. It's really like four-dimensional real space. There are lots and lots and lots of ways that four-dimensional real space can twist. And so we're going to get these complicated tensors telling you how things are twisting. So it's going to get more complicated, but the basic idea is the same. We have a covariant derivative is an ordinary derivative plus something that plays the role of a Christoffel symbol. We can still talk about curvature. We can still talk about all the equations. The only trouble is, because it's matrices and not numbers, matrices have the property that if you multiply them in one order or another order, you don't always get the same result. That means that because of that, the equations that come out are not linear. And what that means is that the force fields act on themselves. So if you have two beams of light, they'll pass right through one another. If you have two beams of pi mesons, they won't pass right through with one another. They will act on one another. They don't just act on neutrons and protons, but the actual fields, the pi meson fields, will act on each other. And that makes it much more complicated. Okay. Only one thing wrong with this theory. It's not quite right. The trouble is, neutrons and protons are not fundamental particles. Neutrons and protons are actually made up of quarks. And the people who pushed the quark idea were Feynman and Gell-Mann. And the idea is, you've got these different kinds of quarks. The main ones that make up ordinary matter are up and down quarks. And that a proton is a composite particle. It's made up of three quarks, two ups and a down. A neutron is a composite particle. It's made of three quarks, two downs and an up. Mesons are composite particles made up of a quark and an antiquark. So it's not true that the protons and the neutrons are the basic piece of matter and the mesons are the fields. They're all made up of quarks. But you can still do the same kinds of deals. Instead of thinking of the neutron and the proton as being two states of the same basic object, you think of the quarks as being, the up and down quarks as being two states of the same basic object. So the same kind of geometry comes through even though the details are messed up. So the people who put together what's now called the standard model of subatomic physics is our own Steve Weinberg and Abdus Salam. I think got the Nobel Prize for that. And the features of the Standard Model is that when you have a quark, you should think of it as being part up and part down. So everything we said about 2 by 2 matrices still goes through. And you've got this, the buzzword is SU2 for these 2 by 2 matrices that mix the up and down quark. The same things also mix electrons and neutrinos. And there's something to do with left-handed and right-handed that I don't want to get into, but there are extra details to be filled in. But you have this 2 by 2 bit that these basic fields give rise to. And then the quarks themselves have an extra symmetry called color. It doesn't really mean that they're red or blue or yellow in the sense that ordinary light is red or blue or yellow. It means that there are 3 states, and we got to call them something, so we might as well call them red and blue and yellow. And so when you have a quark, even if you say it's an up quark, you have the extent to which it's red, the extent to which it's blue, the extent to which it's yellow. That gives you, it really is described by 3 complex numbers, and those will twist among themselves. And now instead of having 2 by 2 matrices, you're going to have 3 by 3 matrices. So the buzzword for that is SU3. And everything in sight is a complex number, and you could twist the phase of that complex number around, and that's called U1. And so the Standard Model is things based on the group SU3 cross SU2 cross U1. And so it has particle content. SU3 has 8 kinds of fields, and those are called gluons. Those are the things that carry the strong nuclear force. This is what holds a neutron together as a single unit, or a proton together as a single unit. You've also got the 3 fields for SU2 and the 1 field for U1. I would like to say the U1 is electromagnetism. It's not quite right. The U1 mixes with part of the SU2 to give you electromagnetism, and so you get light particles out of it. And then you also get these particles W plus, W minus, and Z that carry the weak force. And it was really for working out the details of this mixing and how that all holds together that was the electroweak unification. You're saying that the weak force and electromagnetism are really 2 aspects of the same thing, of the SU2 cross U1. That was the key to the Weinberg-Salam model. So what's left? About 10 minutes by my watch. It's enough to say what is it that needs to be done. So we've got this Yang-Mills theory, but all that Yang and Mills said was write down these covariant derivatives and play with them. So you get some field equations. Now that's taken into account. So what needs to be done is it doesn't explain why nuclear forces are short range. Remember there was this business about the mass gap. If you just look at the equations, it looks like gluons should have no mass. But yet everything is short range. So why are the nuclear forces really so short range? In particular, why are there no massless particles that come out of these interactions? That's the mass gap problem. And a related problem, it's not exactly the same problem, but a related problem is why is it that you never see a quark? You see triples of quarks as neutrons or protons, or you see a quark anti-quark as a meson, but you never see a single quark. So you see quarks all put together in composite particles that have no net color. You put red and blue and yellow together and you get white. Or you have red and anti-red, or blue and anti-blue, or yellow and anti-yellow. The only particles you see in the world as macroscopic, well, not macroscopic, but as detectable stable particles, or even not so stable particles, are composite. Why don't you ever see bare quarks? That's the confinement problem. Why is it that one quark pulls another so that they always just form these clumps of three quarks, or one quark and one antiquark? And neither one of those is really understood from the physics end. Then the essential math problem is that all of this didn't use quantum mechanics, but quantum mechanics talks about what is the wave equation for this particle or that particle, the other particle. It assumes that you have a certain number of particles and you have a wave function for each particle. Quantum mechanics has no room for emitting a new particle. The number of particles in the world changing. If a proton turns into a meson plus a neutron, the number of particles has changed. That doesn't fit into quantum mechanics. Quantum mechanics per se can't handle that. Now there's an extension of quantum mechanics that can. It's called quantum field theory. Quantum field theory allows you to have particle creation and annihilation, but quantum field theory has its own difficulties. The biggest difficulty is that if you sort of follow your nose and do a calculation, I guess I talked too loud and wore it out. Okay, is that better? So, if you do quantum field theory, if you try to do some calculations, what you get is you figure out the answer to something. Oh, that's 1. And then you figure out the correction to it. Well, that's an extremely small number times infinity. Oops. You get infinities all over the place. Now, there are ways to deal with the infinities. You basically... the infinities have to do with there being particles with extremely high momentum. And you say, well, we just won't allow things to be that high momentum. We'll either put everything on a lattice where, remember, momentum had to do with wavelength. So if you don't allow things to have very, very short wavelength, you don't allow very high momenta. So if you put things on a lattice where there's a certain minimum distance, that means you don't get very, very high momenta. So you tweak the theory to get rid of these terms, but then you get something that isn't the correct theory. You have to cut things off and then readjust your parameters and then allow higher momenta and then readjust your parameters and then allow higher momenta and readjust your parameters and take some appropriate limit as you allow higher and higher and higher momenta, and at the same time you're adjusting your parameters so as to keep everything right in the low energy limit. This is called renormalization. And it is worked out in full mathematical detail only for some very, very simple models. Models in 2 dimensions, scalar field theories. It has not been worked out for gauge theories. Even gauge theories, if we pretended that the world, instead of being 4-dimensional, was 3-dimensional, that makes life easier. Even there, it isn't fully worked out. So, problem for $1 million is the mathematical problem, 2 parts. The first is to, for what's called a simple Lie group, for example, SU2 or SU3, to show that there does exist a fully renormalized quantum field theoretic version, not just quantum mechanics, but quantum field theory, quantum field theoretic version of the Yang-Mills equations, or of Yang-Mills theory in 4 dimensions, with the structure of this group built into it. And not just that, but show that the only excitations that come in this theory have a certain minimum energy. And minimum energy is the same thing as minimum mass, because E equals mc squared. Energy is mass times speed of light squared. So the idea is that you have the vacuum. How much energy does the vacuum have? 0. Now if you have 1 particle with mass m, how much energy does that have? mc squared. What about a 1 particle with mass m that's moving? Well, then it's got mc squared plus kinetic energy. So you've got 0 energy and then mc squared and then more. By having that particle move, or by having 2 or more particles, you can have more energy. So if all the particles in the theory have a non-zero mass, then you have this gap. The vacuum has 0 energy, and then all other states of the theory have energy above that. Now, I told you that in quantum field theory, you allow creation and annihilation of particles. The number of particles isn't really well defined, so you can't say this particle and what's its mass. But you can say a state of the system. What's the total energy of the state of the system? And you can say there are no states of the system with energy in this interval. That aside from the vacuum, the only state, all states of the system have energy of at least some number delta. And that's proving the existence of a mass gap. So if you can do those two, you got your $1 million. That's it.
You also have to convince the Clay Scientific Board, and beyond that, you have to get it published first, and then convince their scientific board, and then convince their financial board. But then you'll get your $1 million if you're still alive. Thank you, Lorenzo. Are there any questions?
Yeah.
You talked about particles and waves. If things are like waves, what is it that's waving?
That's a really, really good question.
Everybody here, let me just repeat.
Oh, sorry.
It's a question of what is waving in the waves.
Right, this was a big question in the 19th century that Maxwell wrote down his equations for electromagnetism and showed that electricity and magnetism supported waves, which he interpreted as light. And the question is, what is it that's waving? And so people said, there's this object called the luminiferous ether that is waving. And people tried to do experiments to figure out how fast we're moving compared to the ether, because you figure that light should go as the speed of light relative to the ether. Now, if we're walking, if light is moving at 300 million meters per second that way, and we happen to be moving at, say, 10 meters per second that way, and we measure the speed of light, we should only get 299,999,990 meters per second. Now, it's hard to do that experiment, but these two guys, Michelson and Morley, set up the experiment. And they figured out that the Earth was moving at a speed of 0 relative to the ether. Well, that's weird. Well, it could be just coincidence. Let's do it 6 months later when the Earth is moving at a different, because the Earth is going around the sun. Right now it's going in this direction around the sun. 6 months later it's going the other way around the sun. So you should pick up a speed from that. You do the experiment 6 months later and still not moving. Oh dear. What they discovered is that no matter how you do things, the speed of light seems to be the same from any reference frame. And people came up with some fairly outlandish ideas about why it is that the experiment wasn't picking it up. But the answer really came from Einstein, who's, in the theory of relativity, you get different transformations. And he takes as one of his axioms that physics is the same from every reference frame. In particular, the speed of light is the same from every reference frame. And so if there is this ether, it's in no ways measurable. So people never really answered the question, but they stopped asking it. In some ways it just begs the question as well, because if you say that it's a wave of something moving, well, what is that something made of? Well, what would carry the forces that hold that something together? Well, that would be waves of something. Well, what would those waves be waves of? It's a chicken and the egg problem when you get to more and more fundamental. And so, I guess the best answer is that it's not a wave of anything. It's something that is described by a wave function, something that satisfies the same equation as waves of things. So sound wave is a wave of things. It's air molecules moving in a certain pattern, and it satisfies an equation. Well, electromagnetism satisfies the exact same equation, but the thing that you're looking at isn't the pressure of some particles, it's the electric field. And it's something that satisfies the same equation, but I can't really say it's a wave of ether. It's just something that satisfies the same equation. Right? It's not quite an answer to your question, but I think that's as good as you're going to get. Yeah.
Notice you started mentioning group theory and such. How does some of the more
Okay. They tie us into the problem in a few different ways. One way is that the groups that you see in string theory are sometimes more complicated than just SU2 or SU3. You get E8 cross E8, for those who know what E8 is, and that does not include me. But you get more complicated groups is one way. The other thing is that string theory is not a theory of particles in the same sense. It's a theory of extended objects, strings, loops that evolve in time in a particular way. And according to, now they're very small loops. They're loops of an unbelievably small size. But the idea of string theory is that all of the basic particles that you see in the world are excitations of this loop. In the same way that we have you have electric and magnetic media, and their excitations, then their motions give rise to electric and magnetic fields, which is light, and light is particles called photons. So particles have to do with some fields, excitations of something. Excitations of the string, the various different kinds of excitations give rise to all of the particles that we see in the world. And now that's what's happening at a length scale of the string, which is extremely small. And small length scale means very high momentum scale. Very high momentum means very high energy. But, and in fact, what these string theories say is that the world is not four-dimensional. It's 10 or 11 or 12-dimensional, depending on which type of theory you're looking at. And that all but 4 of those dimensions are wrapped up in a very, very tight ball, so small that you can't really see it until you get to super, super high momentum, super, super high energies. But you could talk about what do things look like on a larger scale. If you take a rougher view, you want to get a Yang-Mills theory as the low energy limit of your string theory. So one of the requirements of a good string theory is that if you can solve it and take the appropriate low energy limit, then you should get a Yang-Mills theory out of it. But it itself is a more fundamental structure, but Yang-Mills theory still pops out in the end. Yeah.
As far as physics is concerned, is this a problem? Like, is there any possibility that a guy who figured, or girl who figures this out and wins $1 million we're gonna have to go back and look at physics, physics based on this again, or are physicists in general perfectly happy to keep sweeping?
Those are two different questions, actually. I would say that most physicists would consider the existence problem to not be that serious a problem. That they would say that if you do some formal calculations with Yang-Mills theory, the Yang-Mills theory has a property called asymptotic freedom that says that it really should make sense when you deal with very, very high energies, and then you can ramp down the energy and nothing should go too haywire on you. It may not be very easy to calculate anything, but things should be well defined. So they would say that, most of them would say that the existence problem is a technical problem and not a fundamental physics problem. They would, but I think they would say that the mass gap and the confinement problems are real physical problems. Now, I don't know if mathematicians would necessarily agree with the first statement. And one of the things that comes out of this is, in the statement of the problem, which you can find on the Klein Institute website, there's the statement of the problem written up by Ed Witten and Arthur Jaffe. And one of the things they say is that they figure that a proper solution of this problem is not just going to be throw enough math at it and you'll work out all of the details and it'll come. That to figure out really what's going on, you're going to need some new physical ideas as well. So I wouldn't say so much that solving the problem will then force the physicists to rethink their physics and come up with new physics. Nearly so much as the other way around. In order to solve the problem, we're going to have to understand both the math end and the physics end better. And, well, yeah, that's going to involve rethinking your physics.
Well, maybe it's time for refreshments now. Let me remind you, next lecture is 3 weeks. Tonight we had a lecture about things we could talk, well, things we're made out of, particles. We've had before this two lectures on very abstract pure math. The next lecture in 3 weeks will be on pure logic, fundamental logic. Is P equal to NP, or is P not NP, probably? So, hope to see you all 3 weeks from tonight. Let's thank you.